So now we're going to do problem 2 from online activity number 2. We have a 2-meter cubed rigid tank. Means the volume doesn't change. Contains air. It's being heated from initial conditions of 100 kilopascals in 10 degrees C to 250 degrees C. We want to know how much heat transfer occurred in kilojoules and the final pressure. So we're interested in Qn and P2. So let's start on Qn. So conservation of energy equation, Qn minus Q out, plus work in minus work out, minus the boundary work equals the change in energy of the system. No heat loss. We're assuming there's no heat loss. There's no work coming in or out. There's no boundary work because it's a rigid tank. There's no change in volume. And so this is all we're left with. Qn is mass times U2 minus U1. This is air and ideal gas. The phase doesn't change. And so I could write it like this. CV T2 minus T1. CV because this is delta U that we're substituting for. We'll do it with this equation. We'll not make this assumption. Here we're making the assumption that specific heat is not a function of temperature. But we have table A17 that gives us internal energies of air, so we might as well use that data. So internal energy of air only depends on the temperature. When you go to table A17, you'll see only temperature. Internal energy, remember we talked about is nuclear energy, chemical energy, latent energy, and sensible. For an ideal gas, there's no phase change, there's no chemical reactions, there's no nuclear reactions, and so the only change is the change in sensible energy, which is only a function of temperature. So that's why you don't see pressure in this table. So let's see, we need mass, we need U2, we need U1. So to get the mass ideal gas equation, we can do it at time 1. So mass is PV over RT. Kilopascals, 2 meters cubed. R for air is 0.287. You can find that in table A1. And T1 we need to do in Kelvin, 283. So calculate that and we get, let's find here, 2.46 kilograms. Look up U2 and U1 in table A17. So U2 is for 250, so that's 573 Kelvin. No, sorry, 523 Kelvin. Go there, look up internal energy, and we get about 377 or so. 2.46. Minus U1, which is at 283 Kelvin. And that internal energy is about 202. So Qn. We calculate that, we get 430, something like that, 431. So that gets a box. There's one problem complete. The second part of this was, what's the final pressure? I can either use this mass that we calculated with a similar equation for P2, V2, T2, or I could use this, since it's a closed system of an ideal gas, P1, V1 over T1 equals P2, V2 over T2. The volume didn't change, rigid tank, so volume 1 and volume 2 can cancel. I want P2, so P2 is P1 times T2 over T1. 100 kilopascals times, need to do this in Kelvin, 523 over 283. Kelvin cancel, and we get 184.8. There you go.